Okay, thank you everyone for joining. So today we have one of our own postdocs. He's in the team of Connie Aerts. It's Alex Kemp. And he obtained his PhD not so long ago from Monash University in Australia. And although he is in the astroseismology group, his background is actually not astroseismology. He has his research topic was population synthesis, and that is what his talk will be about today. So please, Alex, you have the floor.
Yep, that's right. So let me know if people can't hear me, but it sounds like it's working. So I'll just get started. For those of you that I haven't introduced myself to yet, yep, I'm Alex. I'm from Australia. And yeah, today I'm going to be basically giving a bit of a summary of my PhD work, which I undertook at Monash University. So this work was done in collaboration with the people listed here. So Amanda Karakis and Andy Casey were my two supervisors. And then also Rob Izzard, Ashley Ryder, Poojan Agrawal, Flor Brugarden, Carol Temminck, Chiagi Kobayashi, and Benoit Cote all contributed to the various works that make up the presentation today. So I'm going to be talking about my work simulating galactic populations of novae. So it would probably help if I laid a bit of a groundwork in both sort of some of the things that I've been researching and also what a nova actually is. So as I said, this is what I'll be talking about today. So this is my PhD work. Before this, I also had some brief projects dealing with chemically unusual field stars in Lamos spectra. And before that, I did some more mathematical work synthesizing gravitational wave merger signals. But as I said, today we'll be dealing with this topic, and this is sort of what I'm working on now, so this intersection of binary cell evolution and astroseismology. So, onto the talk proper. A nova, or a nova explosion, or a cataclysmic, well, cataclysmic variables are different, but a classical nova, or all these terms are kind of the same thing. So a nova is a transient event, an explosive transient that occurs in accreting white dwarf systems, right? So an accreting white dwarf system is sort of shown schematically here. You have your donor star, and it's accreting material onto the white dwarf, so the degenerate core left behind from the stellar evolution of the primary, is in the middle of this accretion disk here, which is green for some reason in this artwork. So anyway, material essentially falls from the companion through the accretion disk and then onto the surface of this white dwarf. So this is, by definition, an accreting white dwarf system. So we're interested in these sorts of systems for many reasons, but in particular, we're interested in them because they produce some very interesting and important transients that are relevant for a wide range of astrophysical fields. So a big one is type 1a supernovae. So a type 1a supernova is essentially when you have a carbon-oxygen core and it undergoes a thermonuclear explosion. So this is, I guess, schematic here is, I guess, the traditional channel for the formation of these, for these transients, right? And these transients underpin our understanding of modern cosmology, galactic nuclear synthesis. They're extremely important to our understanding of the way the universe works, right? So accreting white dwarf systems are at the core of this. They're also relevant in that this may not produce an actual transient, the jury is still out on this, but depending on the composition of the white dwarf here, so whether it's of carbon-oxygen composition or oxygen-neon composition, so this is determined by the initial mass of the primary, what it started with at birth, right? So if it's of oxygen-neon composition, the conventional wisdom is that this white dwarf that's in the middle of this accretion disk, should it reach the Chandrasekhar mass, at which point degeneracy pressure collapses and the white dwarf ceases to become a white dwarf, the conventional wisdom is, rather than exploding in a type 1a supernova, leaving effectively nothing behind, it will instead collapse into a neutron star, right? So in this way, accreting white dwarf systems can contribute to things like, well, potentially gravitational wave inspirals, but at the very least, binary neutron star populations, right, of some of these exotic neutron star white dwarf binaries. And then finally, we come to the actual topic of this talk, which is nova eruptions. So the common theme between these two is that it involves, one way or another, the destruction of the white dwarf, right? It's a thing that happens once, because once it's done, there's no more white dwarf to do anything with, right? The white dwarf is either blown to pieces in the type 1a supernova, or it is collapsed into a neutron star, which is a different object. Novae are different. So a nova explosion is not the explosion of the white dwarf itself. A nova explosion occurs because of the material that is accreted onto the surface of this white dwarf. So if we do this sufficiently slowly, read that as our accretion rate is sufficiently slow, this material piles up on the surface of the white dwarf with effectively the same composition of the donor star, right? So if we're accreting hydrogen material, it accretes as hydrogen. If we're accreting helium, for example, from a helium star, it accretes as helium, right? And then it just sits there until this layer grows sufficiently massive that the base of the layer is sufficiently compressed and heated that a thermonuclear explosion once again occurs in the layer. So in this degenerate environment, this burning is always explosive, and you effectively get a thermonuclear explosion all across the surface of the white dwarf that lifts off the accreted material and produces that very bright optical transient that is detected as a nova explosion, right? So this is how novae work in nature. This is, I guess, the fundamental physics behind what's going on here. So anyway, some fraction of the nova shell is lifted off the white dwarf, right? Some fraction is then reaccreted, and then the white dwarf will have grown a little bit, right? Net cycle. Because the white dwarf survives this process, this happens many, many times during the process of the accretion phase, right? So that's what a nova explosion is. So what are we trying to actually study, and what are we trying to do with it? So the questions we wanted to answer throughout my PhD were things like, how well can, using theory and population synthesis, how well can we predict the rates and distributions of hydrogen and helium novae, and how do these compare with our observations? Right? What are the evolutionary pathways in terms of binary stellar evolution that actually lead to these phenomena, right? And which pathways are most important? And then what role do they play, where they here is the hydrogen and helium novae, in the chemical enrichment of our universe, right? These questions have been attempted to be addressed before, but they've been held back by the limited theoretical knowledge we have as novae from a population perspective, right? So we know how they work on an individual level, but from a holistic binary stellar evolution point, when I started my PhD, this understanding wasn't really there, right? It was all very hand-wavy, and there was lots of expectations, but very few solid tests. Anyway, these are just some of the expectations. So there have been some theories floating around that novae could perhaps produce a lot of lithium, right? There are existing problems in galactic chemical evolution related to not having enough lithium to reproduce what we observe in our own solar system. And also novae have previously been blamed for creating amounts of rare isotopes of carbon, nitrogen, oxygen. Right? This is a characteristic of novae nucleosynthesis. So the way we attempted to answer these questions was using the population synthesis code binary C. So just a bit of context, I'm going to say that most people in this room will be somewhat familiar with traditional 1D stellar evolution codes, such as MESA. So where MESA solves fundamental equations of physics, hydrodynamics, static equilibrium, etc. These population synthesis codes, the way they typically work is instead of solving these fundamental equations, they instead use fitting formulae to the results of these kinds of models to evolve their each star in the binary, right? And then they allow these to interact. And the net effect is you get a very fast way to evolve many systems, all the way from a binary main sequence star all the way to whatever that outcome will be, including all kinds of mass transfer, whether it's Roche lobe overflow, common envelope events. All of this is contained within the scope of the code itself, right? And this is the great advantage of binary population synthesis for looking at this, because so you get this holistic look at the full evolution history of your binaries. Right? And as I said, they do this by relying on the results of the hard work of the detailed theorists. So what did we do specifically? This is a diagram indicating the traditional way that novae have been treated in population synthesis codes. And the reason they've been treated this way, which I'll explain briefly, is because the main thing people have cared about is type 1a supernovae. And the most important thing that novae have to do with type 1a supernovae is that they severely inhibit the growth of the white dwarf, okay? So if you're relying on growing your white dwarf to the Chandrasekhar mass, novae are a huge problem, because if you accrete, say, 1,000th of a solar mass of material, after the nova explosion, you might be left with basically none of that actually on the white dwarf. So very little of it actually effectively grows your white dwarf because it's all blown away in a nova explosion, okay? So novae are a big problem if your channel for type 1a supernovae that you're investigating relies on you actually growing a white dwarf to the Chandrasekhar mass. And for this reason, novae have been limited in population synthesis codes to this one number, this accretion efficiency, they call it, or nova accretion fraction. And what this describes is if we move material from here to our donor star, all we say that is, on average, we assign this to some constant fraction and say that most of it, usually something like 90%, we say is blown away in a nova explosion. So this is the stuff that's lost to the system as a whole. And the rest of it we just add to our white dwarf mass, right? So in this way, we have an easy-to-use free parameter that allows us to control how rapidly our white dwarf grows, provided it's accreting in the nova regime, okay? We have detailed models that do much better than this. They actually compute things like the accretion efficiency, they compute on an individual nova basis, but none of this was implemented in population synthesis codes. And this is effectively what we did. So we replaced this very averaging treatment of novae, and obviously a very arbitrary treatment of novae, with something a little more sophisticated. So this is our model white dwarf in binary C once we were done with it. We had our carbon oxygen or oxygen neon core, so this is the main part of the white dwarf, and we also simultaneously tracked the mass of a helium layer and the mass of a hydrogen layer, depending on whether it was accreting helium or hydrogen appropriately, right? And the idea is that instead of just treating novae in an average sense, we would treat them in an individual sense. So what this meant was that instead of applying the mass just to the white dwarf and then applying an accretion efficiency to it, instead we added the mass to the appropriate mass bin. So say if it's accreting hydrogen, we add it to the hydrogen layer. And then in every single time step, we compare this with the results of detailed nova models to compute something called the critical ignition mass. So this is the mass of hydrogen that is required to trigger a nova explosion, okay? So how much material you need to accrete before you trigger an explosion. This is a function of the white dwarf mass and the accretion rate, primarily. And we do this every single time step. So in this way, we get to track when the novae occur, under what conditions, we get to count how many, and we can start dealing with novae as individual events in a fashion that's comparable to how they're actually observed by observers, right? Rather than this averaging sense where we're only interested in type 1a supernovae. Haven't really discussed this in detail, but suffice to say that there is such a thing as a helium novae. So where a hydrogen novae is defined as something that is basically explosive hydrogen burning, fueling the explosion. A helium novae is exactly the same thing, whereas instead it's a helium burning explosion instead, okay? These are distinct transients, but they have essentially the same underlying physics. The difference is whether you're accreting helium material or hydrogen material, okay? So this is why we track the helium layer as well. Okay, so I think we'll just keep going instead of pausing for questions here. But that's essentially all I'm going to talk about in terms of the fundamental backgrounds of the method that we used, the fundamentals of what a novae is, because I wanted to share with you some of the interesting results that we came along the way throughout that PhD. So the first thing that we did was looked at novae in I guess you could call it a fundamental sense. So for those familiar, we ran what you would call a simple stellar population. What this means is that we essentially ran a burst of star formation, and then we watched it for 15 gigayears. And we counted all the novae, and we looked at what channels they came from, what physics was involved, and what was relied, and et cetera, okay? This was the first sort of experiment that we did. So, and what we found after we watched our population for 15 gigayears and counted up all the novae, was that effectively, one of the interesting results was that whether you care about common envelope physics for hydrogen novae depends very much whether you actually consider that novae erupt multiple times, right? So what I mean by this is, in the left-hand plot, this is a plot that every single hydrogen nova system, so every single accreting white dwarf system that produced at least one hydrogen nova, is weighted equally, okay? So if you care about the binary systems themselves, this is your plot. If instead you care about the hydrogen nova events themselves, accounting for the fact that, for example, different systems will produce different numbers of hydrogen nova events, and therefore this affects your probability of observing the hydrogen nova event from a given system, this is your plot, okay? And what you see is that these do not look the same. So very briefly, a common envelope is a phase of binary evolution that is highly uncertain and involves a rapid tightening of the binary because of unstable mass transfer. Suffice to say, it's a very interesting and uncertain piece of physics to look at. But the takeaway here is that with this very uncertain and interesting piece of physics, do we care about it in the context of hydrogen novae? Well, we find that 85% of our hydrogen nova systems never undergo a common envelope event, okay? So in other words, they are independent of common envelope physics, Okay? So most hydrogen nova systems, they don't do it. Okay? So in that sense, no, you don't really care. But when you account for the fact that actually that tiny 15% of systems that do undergo a common envelope event, they actually produce 80% almost of all novae, right? So if you care about explaining the actual transients, right, then you absolutely care about common envelope physics, and it does matter, okay? And what this is also saying is, of course, that the presence of a common envelope has the potential and tendency to dramatically increase the efficiency of nova production for a given binary, okay? So the ones that undergo common envelope physics tend to produce many, many more nova explosions than the ones that do not, right? This is in some sense intuitive because this is a way of tightening your binary and getting it closer, so you expand your parameter space. Anyway, we also looked at things like the recurrence time between successive hydrogen novae. So this is, in some sense, tied to a specific observable, because observers classify novae as classical novae if they observe one from a given system, but they also have a small number of systems where we observe novae to explode multiple times within a single system, okay? So there's this observational definition of a recurrent nova system defined as a system that has been observed to undergo multiple novae. In practice, almost all novae systems do, but often the recurrence times are of the order of thousands or tens of thousands of years, so far longer than we've been observing the sky in a dedicated sense, okay? And this is the first plot that sort of begins to offer a bit of a window into the different sorts of physics that are lying behind this, right? So you can see that we've got recurrence time, where you've got short recurrence times, so in other words, a short period, if you like, transients down here, and you see that there is a very high tendency to be oxygen-neon composition, okay? This is because more massive white dwarfs have higher surface gravities, so this means that they need to accrete less material before they reach that critical compression. What this means is that you are able to, how to put this? You are much more efficient in your production, so you can produce novae faster for a given accretion rate, okay? So you've got your massive oxygen-neon white dwarfs on this side, and then you've got your tendency of the more common carbon-oxygen white dwarfs over here, which tend to have much longer recurrence times, right? So of the order of, like, that's 100 years, right? So this is where I draw my red line and say anything longer than 100 years, we're probably not going to observe it to undergo twice, just from the history of modern astronomy. Then you've got 1,000, 10,000, 100,000, million, up to like hundreds of millions of years some of these systems have between successive outbursts, right? So there's a huge variation here. On the right-hand figure, we have it colored by instead the donor stellar type, so equivalently, the evolutionary phase of the donor. And what this tells you is also immediately that a lot of our nova systems have giant donor stars, whether they be first giant branch or red giant branch donor stars. So first ascent giant branch is what I'm talking about here, or the more evolved thermally pulsing AGB or early asymptotic giant branch stars. These are tags within binary C. Don't look at them too hard, but you get the idea. Giant donor stars matter a lot, and the reason for that is obviously a tendency, because they're bigger, so they have like a wider parameter space under which they can accrete, but also because they're able to push material harder onto that companion, and the accretion rate matters. If we accrete faster, we reduce that critical ignition mass, and once again, we wind down that recurrence time a bit, so they tend to be more to the left, whereas the smaller radii, low mass main sequence donors tend to be more to the right because they push material less aggressively, their accretion rates are lower, and so it takes them longer between successive outbursts. Right? So all this makes good intuitive sense, but now we have numbers on it. This is a plot that basically shows the same thing, except instead of coloring in by the types, we've got like plots in 2D space. I might actually skip this one, but I'm happy to come back to it if there's questions about it. Okay. So helium novae, this was another interesting result we found on this topic. So if you remember, helium novae are novae that occur under conditions of helium accretion, primarily. We have actually observed one of these ever, so they are a thing, they do exist. But we've only observed one ever, so it's not like we have an actual rate for them to compare with. But anyway, what this plot shows is the final remnant state of these binary systems. So basically, after we watched it for 15 gig a year, what was the final configuration of that binary, okay? They all start off as main sequence. So for the subset that underwent helium novae, we found something interesting, and that is that these intrinsically binary systems, right, that do not involve the destruction of a white dwarf, they end up as single stars, overwhelmingly, right? 95% or something of them end up as single stars by the time that they're done with their binary evolution, which happens usually within 3 years in this case. Okay, so what's going on here? Well, what was going on here is we found that our population of helium nova systems were dominated by helium main sequence donors. So this is a very compact helium-burning stripped star, okay? Which meant that in order to accrete from it, it needed to be very compact. The binary needed to be very close together. And what we found was that ultimately, almost all of our helium nova systems would gravitational wave in spiral, okay, effectively forming a single star by the time they were done. So this was something that no one had ever really predicted or even really looked at before, because no one had done this kind of simulation before, right? Is it true? Is it physical? Does it reflect nature? Difficult to say. But at the very least, it's what we found, and it was sort of a first-of-its-kind kind of prediction, I suppose. And if nothing else, it offers like a good example of some of the interesting things that can fall out of these kinds of simulations, right? We certainly didn't go in expecting this result. But yeah. Okay, so all of that was in terms of simple stellar populations. So this arbitrary starburst, and then we just watch it, okay? Now I'm going to start talking about real stellar populations, so real galaxies, okay? So before we do that, we're going to need to talk about the metallicity dependence of novae. Stars can form at different metallicities, and this metallicity matters a lot for its evolution, okay? And this translates to mattering a lot for its binary stellar evolution. Parameter spaces change, the behaviors change, so we're going to need to account for that if we're going to pretend to be able to model an actual galaxy, because real galaxies don't form at solar metallicity, right? And they don't stay that way. So first things first, metallicity. We looked at, so again, each of these points is effectively the kind of simulation I've just been showing you results from, okay? So we looked at a bunch of different metallicities from 10 to the minus 4 up to z equals 0.03, and we computed what the total nova production, so how many novae and how many nova systems were produced in each of these simulations, okay? So this vague downward trend is something that was already predicted from theory. We already expected high metallicity systems to produce less than low metallicity. The reasons behind this are related to the changes in stellar radii, dependent on metallicity altering your parameter space, and the increased core masses that you eventually get out at the end of your evolution, okay? So we expected this kind of trend, but now we have some numbers that we can actually use when we put it into our convolutions with real galaxies, real simulated galaxies, perhaps I should qualify, okay? So what did we find? We found that there was a negative trend. We found that it affected both the nova systems and the nova events and the nova events per system, okay? So arguably this one is really just the combination of these two, okay? This is a decomposition in some sense. So that was interesting, right? And as I said, this is primarily, or at least what we identified, was this is primarily due to the metallicity's influence on the core masses and also the stellar radii, which altered our parameter space and affected, for example, how many giant branch donors were able to produce novae versus, for example, merge with their companions, okay? So these shifts actually have a relatively significant effect in your number of nova systems. Okay, so I've mentioned real stellar environments a few times now, and now I'm going to break all of your hearts by telling you that they're not really real. They're simulated, and it's not even that complicated a model, right? This is how the convolution works. This is how we go from a very simple star formation at an individual level, right? So we have a single burst of star formation, and how we map that to a real stellar environment, okay? This is what's known as a delay time distribution. So all our stars start at 0, and then we just watch them and we see when the novae happen, okay? This one's colored by the donor type. This is, if you like, representative of a single simulation. So what we did is we get a grid of these, depending on metallicity that I just showed you, with that other plot. And what we do is we convolve this with an age metallicity star formation rate relation. So this one we took from Kobayashi et al. 2020. And what this gives you is as a function of time for your simulated galaxy, so in this case the Milky Way, we have the metallicity and we have the star formation rate. And from this, you can convolve this to get this, okay? So maybe don't worry too much about this. It's just a blur on this scale, but this is the sort of information you can get out, okay? You can get out effectively an event rate history, in this case, broken down into thin disk, bold, thick disk, and halo, because that was the decomposition of the Milky Way that we had access to, of the nova rate. And then if you want to know the current nova rate that we could actually observe today, You just read it off at what at an approximation for the current galaxy age, okay? And this does pretty well, it turns out, but I'll get to that in the next slide. The bottom slide is a more complicated thing that we can now do, and that is that we can now also read off things like the white dwarf mass distribution of our novae, okay? So if I just read off this line, what I get out, and I think I show you one of these plots later, is effectively the distribution of what we expect the currently observable white dwarf mass distribution to be for novae in our galaxy today. This is something that, in principle, is directly comparable with observations, okay? In practice, this turns out to be very difficult to get from observations, but at the very least, we can now make predictions about it. So, progress is progress. So, galactic nova rates, how did we do, okay? We put in this new model, we put in some binary physics, we made our best attempt at getting this binary physics as reasonable as we could at the time. We did okay-ish. The galactic nova rate is highly uncertain for observability reasons. Observing transients in the Milky Way is hard. There's a lot of systematics. Hence, there's a lot of scatter in all these observational estimates, okay? Our estimate lies roughly here. My rough physical-ish estimate on how uncertain this could move, depending on different binary physics, is highlighted in blue, okay? Takeaways. Number one, we are slightly more consistent with something called extragalactic estimates for the Milky Way. So this involves a process of studying distant galaxies, taking their K-band luminosities and then mapping them onto what we think the Milky Way's K-band luminosity is. So this is a technique of estimating the nova rate in the Milky Way. Galactic estimates involve actual observations of the Milky Way. So they have to deal with the systematics of the Milky Way, but at least they're actually observing the galaxy that they're predicting. So, both of these are ways that you can estimate it, and we're slightly more consistent with these ones. We're slightly on the lower end. But as I said, the uncertainties are huge. So how viable would I say matching the nova rate of a given galaxy is to, for example, test binary physics? Not very. The uncertainties are too big, right? We can't see anything here. If I alter my binary physics and I end up here, am I more consistent? Am I less consistent? Right? It's not a useful benchmark, okay? This was one of the main conclusions from looking at this stuff, okay? And at least part of this is due to observations, but also part of it is just due to how swingy it is with physics. At the very least, it tells you that you're roughly sane, but it's hardly a resounding confirmation of our understanding of binary stellar physics, okay? We also looked at M31, so this is Andromeda. Brief, interesting story. This was the estimate during my PhD. This was the estimate 5 days after I submitted my PhD thesis. So I had great fun saying like, oh, we do okay for the Milky Way, but we don't do such a good job for M31. And then 5 days later, a paper was released that lied perfectly on our predictions. So that's just how it goes sometimes. But at any rate, this is an example of us playing the same game with another galaxy, and once again, we find something that's relatively sane. So once again, takeaways, yes, there are uncertainties, yes, they are large, but at the very least, it looks like, in the case of novae at least, we appear to be able to make relatively sane predictions of nova rates, which, given the amount of physics and stuff that we have to go through in order to reach this, is a little surprising, to be honest. And I think it's fair to take away from this that maybe what this really means is also that novae may not be a super good test of binary physics, at least when you're only looking at the nova rates, okay? So what else can we look at, right? So I alluded to the fact that we can also make predictions about distributions observable today, okay? So this might be an example of a better probe, okay? So rather than looking at the nova rate, we start looking at the distributions and seeing how they affect. So on the left, we have, for example, a distribution of the white dwarf mass from our work, okay? Predicted as we expected to be observed today. And now this very different distribution is another estimate that is sort of observationally derived, okay? There's a lot that goes into this, and if they hadn't, let's just say this is far from model dependent. It's actually very model reliant, which makes it a somewhat difficult thing to compare with, because it's unclear whether you're really comparing with, for example, discrepancies between the models or discrepancies because you've done a bad job fitting this, reproducing this galaxy. But at the very least, it indicates that unlike the nova rate, the nova white dwarf distribution does perhaps show some promise as a useful probe of things like binary stellar evolution and the star formation histories of individual galaxies, which is actually a pretty cool result. This is just another example of the sorts of interesting things you can do. So this is a breakdown into thin disk, bold, thick disk, and halo of our Milky Way, and where we expect our novae to appear. Okay, very few in the relatively dead halo, lots in the thin disk, decent amount in the bold, and again, once you go into the deader star-forming environments, such as thick disk and halo and so on, your nova rate really does take a bit of a nosedive. It also highlights that you get some systematic differences in terms of the fractions of the different accretor types and donor stellar types as well. So these are somewhat minor. It's certainly interesting that first giant branch stars are so ubiquitous among these very different star-forming environments, right? The star formation history for the halo is very different to what it looks like here. And yet, first ascent giant branch stars turn out to be very important for novae in both of those cases. Okay, so that's results two. We looked at some real galaxies, and we looked at some distributions, and we made some conclusions about how useful we expect novae to be for applications like probing binary stellar physics, probing different star formation histories for distant galaxies, right? And the general conclusion is, well, if you use distributions and you can actually get them, then yeah, they might actually be useful. But if you're relying on rates, it's perhaps less useful. So then we moved on to a different question about novae, which was, what is their role in galactic chemical evolution? Okay, the origin of the elements. What do they contribute? Traditionally, the answer has been very little, and they're typically ignored from such codes. Okay, almost exclusively, in fact. So the way that this roughly works is, instead of using the delay time distribution I showed you earlier, we now convolve something called an ejector delay time distribution. So instead of weighting each nova eruption equally, right, obviously subject to its birth and the system, et cetera, but effectively treating each individual nova eruption equally, we are instead weighting them by the mass of ejector they put out to the interstellar medium, okay? So now we're accounting for effectively different masses, ejector masses, per nova explosion, and we're accounting for that. Then we effectively convolve this with using the detailed chemical evolution code Omega Plus. We convolve this with different theoretical and, in some cases, observational yield constraints for novae. And then we get out, well, not a question mark, we get out actual plots, okay? We get out histories, once again, for the Milky Way, we did this for the mass of different isotopes that we can then compare with other stellar sources, and then we can then compute abundance fractions for and compare with observations, for example, within our own solar system. So this is an example of, for example, comparing AGB star yields, right? Type 1a supernova yields, massive stellar yields with 3 different nova models, okay, for a bunch of different isotopes. So you've got helium-3, helium-4, et cetera, and the general conclusion that we reach is that, with the exception of carbon, nitrogen, and oxygen, specifically the isotopes nitrogen 15, carbon 13, oxygen, I believe was 18, not 17, but I might have that around the wrong way, I actually can't remember. Novae don't contribute at significant levels, basically. It's negligible, less than 1%, right? Very small. These percentage, now, yeah, there we go, oxygen 17, I've got it written down. Right, so what this number is means, depending on the nova model we use for the nova yields, between 7.7 and 13% of all oxygen 17 in the universe at the time of the formation of the solar system is expected to have been produced through novae. Well, not the universe, the galaxy, but you get the idea. Right, correspondingly, 21 to 36% of nitrogen 15 and carbon 13, 8.3 to 36. So even for the ones where it contributes significantly, it's not dominant, right? So can you afford to ignore novae in your nuclear synthesis models? Yes, unless you care about lithium. Lithium, we found a very different result. So this is something that just fell out of our models, essentially. This is not a result of trying to tune or adapt or whatever buzzword you want to use, we didn't do it. This is not something we were super expecting, but when we use the observed, so when we look at actual nova ejector and we observe and we measure the abundance of beryllium-7, so this is the radioactive isotope that decays to lithium-7, so it's effectively an analogous to lithium-7 because of the short half-life and one-to-one decay probability, effectively. What we observe is that novae, when we account for them in our galactic chemical evolution models, perfectly reproduce the solar lithium abundance, right? So the abundance of lithium-7 that we detect in meteorites in our solar system today, okay? This has historically been a very difficult nuclear synthesis problem to solve. Novae have been proposed for this for a very long time, but the first detection of beryllium-7 in nova ejecta didn't happen until 2015, okay? So only 6-7 years ago. Until then, all we had were theoretical models, okay? Yes, I'm aware that this is obviously, some of these are after 2015, but the point is that not much has changed in this space since in terms of the amount of lithium we expect them to produce, okay? There's a huge mismatch between how much lithium our theoretical models, which historically is all we had for this, and how much lithium we actually see novae producing when we look at their ejecta, okay? And when we use the observations combined with our theoretical nova populations, as I said, we reproduce the observation very well. This mixing thing is a detail, but suffice to say it's a free parameter in our model, and we appear to be robust to it. Whereas the theoretical models do not, okay? The theoretical models all sit above this line, and it barely budges, which is more or less the findings of previous studies which have relied on that anyway. So yeah, this was, I guess, a key finding of ours, I suppose, that novae, where we were able to demonstrate that combining theoretical nova populations with observed lithium abundances, the problem sort of disappears effectively. And this is also including all the other sources as well, right? So it's not like we're going to have an overproduction of lithium anytime soon. These error bars are 1 sigma on the uncertainty in the lithium abundance in nova ejecta, which we identify as the primary source of uncertainty in our model. Oh, no, in the model, in the, I guess, the state of the field, basically, in terms of the lithium abundances. So hopefully, as time goes on and we get more observations of different novae with different beryllium-7 abundances, hopefully these error bars go down and we can maybe even potentially use lithium to start tuning our models. Anyway, so that's the end of the talk. So as I said, we found that common envelope physics was particularly important to the nova systems which produce the most novae. So that's when you should care about it, if you care about the nova events but not the nova systems. There's the result that we expect most of the novae in the Milky Way to be in the thin disk. We have a few predictions for galactic nova rates, and they're sane. We find that we do not do the mass distribution of observationally derived studies. As I said, this is most likely due to physical differences between the models assumed within these studies and the fundamental differences in the models that we assume. But at the very least, it highlights that the white dwarf mass distribution is something that is sensitive to your physics, which is actually very useful to know. And then with galactic chemical evolution, we found only these isotopes had non-negligible contributions from novae. So thank you for your attention, and that'll be the end of the talk.
Thank you, Alex, for this very nice talk. Are there any questions?
Oh, hello. Hey, Alex. Thanks for the nice talk. I have like a bazillion questions, so I have to restrict myself.
Okay. We can always chat later as well. So yeah.
Regarding modeling, so you said when you accrete low enough, you get novae. So there's actually this thing that more or less if you accrete a bit higher, you get steady accretion. If you get a bit higher, you expect a runaway growth into a giant.
Yes.
So how do you incorporate that into your models?
Yep. So from the detailed models, we take prescriptions for these accretion regimes. So we set a white dwarf mass dependent ceiling, essentially. I don't have a plot for it, but I can't remember which model we drew it from, but we have a separate ceiling for hydrogen and helium, obviously, because it's very different physics. But effectively, above this accretion rate for a given white dwarf mass, we say, yes, it's steady accretion, so we accrete perfectly. And then within that, obviously, there's a gap where we are able to accrete and the material is able to be burned stably in the surface. And then, as you say, beyond a certain point, you get to a regime where you effectively are unable to, the white dwarf is unable to accept the material, and yeah, it effectively piles up in a giant-like layer. So we use an optically thick wind prescription from Hachisu. So effectively, the material on the white dwarf so we accrete the material onto our white dwarf at the maximum steady accretion rate limit. So effectively, the upper limit of the steady accretion rate regime, and then subsequent material that is piled up is blown away, or assumed to be blown away, I believe, in a spherically symmetric manner from the white dwarf. So it's lost in an optically thick wind is the short jargonier way of describing it.
Okay, thanks. I guess just one more. So regarding recurrence times.
Yes.
So what observational constraints do we have on recurrence times?
We know that we have observed some that recur. In fact, if I go to Shara's plot, there they are. There aren't many. So what observational constraints do we have on the recurrence times? We know that they are able to recur very quickly. We have observed something like a couple of months recurrence times in the most extreme systems. I think it was T-Pix or something. So we know that we have some constraints, or at least indicators, at the extreme low recurrence period. It probably helps if I have the other plot up now. We have some constraints at this end, okay? So we know we can get sub-year recurrence times because we've seen it, basically. We've seen our novae recursively explode with a period of a few months. At the high end, obviously we have none because we've only been really watching for like the last 100 years ago, hence the red line. But there are some constraints. Is it a well-populated space? No. Do we have the sorts of information that would allow proper comparison with the kind of information? No, that's the benefit of theory, I guess. We can always dig out the lovely physics relatively easily, where the observers have to really work for it. So it depends what you mean by constraint, I guess.
Okay, thanks. I guess at least masses are consistent with oxygen, neon, magnesium white dwarfs.
Oh, right. In terms of, are you asking, do our recurrent nova systems tend to be massive? Yes, exclusively.
Okay, any other questions? First, give priority to the young.
Hi. So you showed a figure with like the relation between the nova rates and the nova systems and the metallicity, right? Did I get it?
Yes, I know the one.
So did I get it correctly that is because the metallicity influences like your core size?
Yes. So I brushed over this, but
yeah, so what about other effects that influence your core sizes? For example, convective boundary mixing, which also can have quite a large impact on the size of your cores. Is that like included in your model uncertainties, or?
Excellent question. So what we deal with here is we have specifically looked at the influence of metallicity on stellar evolution. So binary C, like I'm going to say most population synthesis codes, it relies on single stellar evolution tracks that are must be 25, almost 30 years old now. So they're from Pohl's 1998, I believe. So what this means is that what we're really doing here when we vary the metallicity is we are swapping out our stellar tracks, going like that Ono poles ran 25 years ago. So we're not, for example, running different, for example, MESA simulations. As I said, these codes do not run physics. They run, they basically can, but they can change between the fitting formulae to these different metallicities. So basically all of the metallicity dependent physics, so all the physics that was in Ono Pohl's models is by proxy and transfer within our models. Do I recall exactly what convective boundary mixing Ono Pohl used? No. I know that they use quite a high overshooting factor. That is something I remember, but I don't remember precisely how they treat things like convective boundary layer mixing in detail. But yes, the metallicity dependence of that, for example, with the different opacities and things, is contained within the model. So anything stellar evolution related is in there to the extent and with all the restrictions of Ono Pohl's modeling back in 1998. The reason I'm also kind of emphasizing this is that one thing we did not account for in our models, metallicity-dependent models, is metallicity-specific novae microphysics, for example. So the change in opacity from the accreted material onto our white dwarf, okay? And this does have an influence, but it's secondary. Right? There has been actually a study, a really good one, that looked very specifically at the metallicity influence on nova microphysics and comparing the differences between what we looked at, so that's the influence of metallicity on stellar evolution, and then the influence of metallicity on the nova microphysics. The stellar evolution dominates, basically, or it appears to.
Thanks for the talk. But it's not only the recurrence time, but also the supernova, so the nova occurrence rate. And is that observational constraint, or is it observational well constraint?
Yeah, there are observational constraints on the nova rates. So each of these is a it actually goes all the way back up to a Hubble paper, actually. But there are definitely observational constraints. They don't have to be consistent with each other, but yes, people observe nova rates in galaxies and lots of different stellar environments, and that is something that is a constraint. So that's the purpose of our convolutions and everything, to turn what is a useful plot to look at, for example, the fundamental physics of, for example, which channels matter per burst of star formation and so on, into something that is comparable with, in principle, comparable with observations, at least minus selection effects and so on. That we leave to the observers to correct for. Does that sort of answer the question?
Yeah, okay, thank you.
Awesome. Yeah, just to be clear, each of these, this plot specifically is not comparable with observations. Each of these is effectively a single stellar population, like I was showing in the first results section. And yeah, we don't have like maybe you could contrive something out of globular clusters or something at different metallicities, but no, this curve is not observationally constrained except by forward modeling and so on and inference.
So you solved the galactic lithium problem.
At the very least, we demonstrate that novae might be a viable solution.
So the problem now is that there has been a lot of nova modeling, and there is a lot of effort going into measuring the reaction rates that went into those models. So the question is now, where did they go wrong, do you think?
Sorry, say that again. Where do they belong?
Where do the models of novae go wrong, that they don't predict the amount of lithium that comes out of the observation? Because
that's a good question.
People seem to have covered most of the uncertainties, so it's very curious that.
Yeah, I agree. So I agree that the models are definitely inconsistent with observations by a ridiculous degree. Where do they go wrong? I don't know. Lithium is a pain in the neck element. It is it is a notoriously difficult element to model, and all I can say is that you would think that it would be very sensitive to physical choices. This is something that's been established certainly for a long time in the AGB community. Where do they go wrong? I don't know. This was, I think I ended my PhD in a bit of a call to arms to try and solve this, but as you say, they're already trying. Where do they go wrong? I don't know. I will say, though, that it is interesting that there has been all this work and not one of them has come that close, basically. So in all the theoretical models and everything, they are all severely under-predicting, whether it's from Starfield's group, Jordi José's group, the Rakea paper, which actually resolved different mass accretion rates. So this one was a personal favorite of mine, this particular work. None of them, so there isn't that many, by the way. There's like 5 ever, but of these detailed nuclear synthesis papers. But yeah, none of them have really solved this. There's been suggestions about ways to do with helium mixing and things. Yeah, it's ongoing mystery and discrepancy. And simply because it appears so difficult to reproduce this, it does, again, sort of imply that this could be a very useful constraint, at least regarding nova microphysics, okay? When something's hard, there's always a silver lining if you look at it the right way.
Okay, any more questions?
Thank you for your talk.
Sure.
I have a question that's more like something you said in the beginning. So you look at the, you have both limit masses for hydrogen and helium, right? And you sort of,
yep. So you're talking about in the fundamentals of the NOVA treatment?
This slide. So you sort of said that you look at whether the white dwarf is accreting hydrogen or helium, but I would think that they are accreting hydrogen and helium at the same time, and that is sort of mixed together. Would that change your results?
No. So because what I said was an oversimplification. When I said accrete hydrogen and accrete helium, I did not mean they accrete pure hydrogen, and I did not mean they, well, actually they do. When they accrete helium, it is basically pure helium. But no, what I'm really talking about is hydrogen. I meant solar composition, so, or whatever the composition of the donor star is. So that's what I meant. So in terms of what you're talking about and why it isn't a mix of so on, that's because hydrogen's burning conditions are much lower. You require much less lower temperatures, lower densities than helium, okay? Helium is much more, you need more extreme conditions in order to burn helium than hydrogen. What this means is if you accrete solid composition material, you will not get a helium explosion. Well, actually, okay, let's not go there. You actually can, but you will not, if you've got a well-mixed combination of hydrogen and helium, where you're dominated by hydrogen, it'll be a hydrogen that explodes, always. It's like an order of magnitude in discrepancy. And for example, the critical ignition mass diagrams, right? So you'll always reach that condition for hydrogen ignition first, provided you actually have hydrogen to ignite. Very briefly, the caveat that I said I wouldn't talk about, but I might as well, is that if we're burning hydrogen, we're making helium. So if we're making helium and then we're depositing helium, then there is in fact the potential for a hydrogen accreting object to undergo a helium novae in the technical sense. This is something we actually treat in a very, in our analysis, we treat very differently to the other source of helium novae, where you accrete helium, for the simple reason that detecting helium novae is kind of hard, right? So if we have a hydrogen layer on top of our helium layer, when the helium layer goes off, it's probably going to be pretty hard to identify that as a helium novae, simply because it'll be mixed with all this hydrogen, right? So it'll probably just look like a weird hydrogen nova. So for this reason, I feel like it's all right to make the oversimplification where we just, from an observational perspective, call helium novae from helium accretion. But this is it does get a little gray in the middle. But yeah, but if we're well mixed, then no worries, it's always a hydrogen nova.
Okay, thank you.
Okay, I think we can close here. So let's thank Alex again. Thank you very, very much.